Hi there, and welcome to this new and exciting session in which we'll see how to extract automatically this kind of table into an Excel sheet. So if you've ever wondered how it's possible to programmatically get this table and transfer it into an Excel sheet like this, then you are at the right place, as we are going to make use of the Python programming language together with the Paddle OCR library, which contains text detection and recognition models, which we are going to use to extract this information and then later on structure it out such that we obtain the table we have right here. Don't forget to subscribe and hit that notification button so you never miss amazing content like this. We are going to start by looking at the different steps we are going to take to produce our PDF table to text extractor. The very first thing we'll do is start by detecting the table from the PDF, which is in the form of an image like this. So we'll go and detect the table in this image or in this page, because we have several pages. So we will go page by page and then detect each and every position where we have the different tables. So you could see here, you see this table that has been extracted, this other table which has been extracted, and then from here we are going to move on to carry out text detection. So once we've detected this table, you see this table here, we will now detect the positions or the locations of each and every text in this table image right here. So you can see we detect that there's component, or rather we detect that there is this image, or there is this text at this position, there's text at this position, and so on and so forth. And then from here we move on to text recognition. So we want to recognize the text which has been detected. That said, we get here and then we recognize each and every text we have here. Now you just see from here that we have selected this line. You see beverages, alcoholic and non-alcoholic, the FCT score, the updated FCT, and then this difference. So at this point we've already recognized the text, we've detected and recognized the text. The next thing we want to do is bring out this text in a way that we could represent it in some Excel table. Now to do this, we are going to make use of our table recognition, or rather table reconstruction model. So for table reconstruction, what we're going to do is we are going to draw some let's say we have this lines here. You see we have this horizontal lines for each line, and then we have this vertical lines for the columns. Now at the intersection of these lines, we are going to get the text which is found there and then reconstruct this CSV file you have here. So what this means is, after carrying out the detection and the recognition, we know the exact positions of each and every text, and then we make use of this intersection to compare this intersection position with that of each and every text we have here, to be able to get the exact text which is found at this location, and then be able to reconstruct our Excel or our CSV file here. So you see data sets extracted, this extracted, this line here, you see there, this row, and then the next row reconstructed, and so on and so forth. So you see how we are able to get from this here, from this initial image or this initial PDF page to this Excel which is right here. Now let's go ahead and see how to bring this project to life. The PDF we shall be using as example here will be this one, Journal of Food Composition and Analysis. So here we have this 5-page PDF here, you see 5-page PDF, and then we are gonna see how to extract this different text in these tables. So the first step we'll have here will be to convert each and every page here into an image. So this will be an image, this an image, this and this will be an image. Now to convert this PDF into the image, we're going to make use of this PDF to image library right here. So here we go ahead with installations, pip install PDF to image, and then we're going to install popular utils, which will be useful in making this PDF to image work. So we'll simply run this, and that's it. We're done with the installation. The next step will be to go on to convert this PDF we have here into the different images. So we have from PDF to image, which we've already installed. We're going to import convert from path. So we have this image here, this PDF here, which is in a given path, and then let's run this, and then we're gonna take the images from there. So we have images equal convert from path, and then we simply specify the PDF path. So there we have test.pdf. We run that. That should work fine. Convert from path not defined. We have convert from path. Okay, so that should be fine. And now we have our images. We're going to store those images in a given directory. So let's make that directory. We just have make dar, and then let's say we have pages. So we make the directory, and you can see that here. See, we have this pages directory, and then we're going to store those images in our directory. So we have for I in range len images. Basically we're getting all the different images. We'll simply do for every image, we'll save that, and then we'll specify the path. So here we have pages, and then we have the page. So we'll give this a different name, making use of this I right here. So here we have the page, as we said, and then we'll add this, we'll attach that to the page name, and then we'll specify here that it's a JPG file. Now our encoding scheme is JPEG, so we have JPEG. Okay, so we run that and everything should be fine. That's great. We open this, and this, you see page 0. That should be fine. Let's open this, say page 2. Let's open up page 0. Okay, so that's it. You see, we have this image now. We have page 2. That's it, and the others are in a similar manner too. So you see how we've left from this here, this PDF, to the images. Okay, so that said, we now move on to the next step, which will involve extracting the tables from these different images. In this next step, we'll make use of a deep learning model which has already been trained on a very large data set, which is the pop layout net data set. Now the way the different data points in this data set look like is as we have here. We have an input image like this one, and then in the output, or as output, we have different locations for different elements in this image. So for texts, you see here text in blue, and then the titles are in purple. The lists, we have no list here. The tables, you see the tables are in red, and we also have the figures, which are not here. There's no figure here. So basically what this deep learning model is going to do is it's going to learn from hundreds of thousands of these kinds of images and the corresponding outputs, such that when now given a new image, it's able to detect that there is a table found at a given position in the image. Right here on this IBM platform, you could see this pop lay net description, and you could get a sense of the number of and you could get a more precise idea of the number of images used. So you see here we have 358,000 images broken up into training, validation, and testing. Then you see the different sizes. This is 102 gigabyte. Now let's check out this paper. This is the official paper, and you could see this descriptions here. So here, let's scroll this way. Here you see how the PDFs or this image has its layout presented to you, and this layout now can be used to train a deep learning model. Now, if you're new to the topic of deep learning, you could feel free to check out our platform where we have several courses on deep learning and applying it to solve real world problems. You could also check out our YouTube channel by clicking on the different links we have here in this free playlist page. Now, the pre-trained layout detection model we'll be using will be from the Paddle OCR project, which you can have on GitHub. So here we have several tools for OCR, and one of them is the layout detection. We should check somewhere here. We have layout. You see, you have layout information about the layout detection, and as we move on in this course, we'll see how also to do text detection and text recognition while making use of already pre-trained models available on this Paddle OCR project. So that said, let's go ahead now to see how we can extract these tables from the image, which is from the PDF. That said, we'll go ahead and install our layout parser from the Paddle OCR tool. So we have that. And now before we move on, we're gonna get back here to this GitHub repo, and you'll see we have this quick start where have this image defined. So you read the image and then you actually build the model, and from here you detect the different, or you detect the layout or extract the layout from this image. Now you notice that here we have this configuration path where they specify the model which is being used. It's here PPYOLO v2 R50, which stands for ResNet 50, for those of you who have already some background in deep learning. And then we have this threshold. Now the reason why we have this threshold is because the model detects a table like this one with a given probability. And so when we have a threshold of 0.5, we're saying that if a table like this one is detected with a probability of greater than 0.5, then we'll consider that detection valid. Whereas if it's less than 0.5, then we would not consider that detection valid. So that said, we get back here. We have this label map to specify the different labels we can have, either text, title, list, table, or a figure. Here, if we were to use CPU, by default this is false. And then here we have the Math Kernel library by Intel, which is used for the acceleration of deep neural networks. DNN here stands for deep neural network, and MKL stands for Math Kernel library. So by default this is true. Now talking about the MKL DNN, the MKL DNN, which as we said is Math Kernel library for deep neural networks, is used for accelerating deep neural frameworks. And talking about deep frameworks, the specific one we're using here is Paddle. Now, or maybe you may have been used to working with other more popular frameworks like TensorFlow or PyTorch, but you could check out Paddle, and most especially this Paddle OCR repo, which has many pre-trained models readily available to be used. So that said, once you define your model, or once you load your model, the next step will be to carry out the predictions, and from here we could go on to extract just the tables. So we'll just get this here. Let's get this and then paste this out here. Okay, so that's it. Now our image we have in here, we're gonna take this page 2. Basically you could do a for loop to go through each and every page. So you could always do that. So here we have this page 2, and then let's copy its path. So copy path, and then there we go, we have this path here, specify, and then this pre-processing right here. Once this is done, we go ahead then to pass this in our model. So as we've said already, we have a deep learning model here which has certain parameters, and then during the training, that's after this model has been trained with about 358,000 different inputs and outputs, the model now learns to get an input and predict reasonable outputs. And that's basically what we're doing here with this model.detect. So this model has already been trained, and so from here we'll just run this. So we get in no model name Paddle OCR, so we'll go ahead and install this. Now another installation, we'll go ahead and start by installing the Paddle, the GPU version. We'll install Paddle OCR, protobuf, and then we'll clone this Paddle repo. So let's run that. Now we have this installed. Let's get back here and rerun this. Rerun that. We now have our layout generated. You should notice that this model was downloaded here, and it's about 221 megabytes. And then we have our layout. So we run that, and this is what we get. Now you'll see that here we have this layout right here, and then we have information like this one here. You see block, a text block, rectangle, and then we given the exact position of this text. Then as we move, you see we see it's type text, then the next text block again, then the next text, and let's just search for table. So let's search for table. Okay, so that's it. So here we see we have type table. Now this type table, you see the score 0.97, and then we have its position. There we go. We should have this actually is position. So that's it. This is position, and we should have another table block. So if we search again for table block, table, let's search here. You see we have this other one right here. Now to verify that we actually get in a table, here you see we have this type, and then we have its coordinates here. So let's open up the image. That was the page 2 as an image. See, it's a JPEG, and then we could get the image height and the image width. So if we get to this point, now you could check this out here, the coordinates. So first thing you should notice, if you have this image, this position right here is a position 0 0. So the top left corner is a position 0 0. You could see that here. As we move, we go towards 0. You see 0 0 6. Anyway, just note that as we here, that's 0 0. To obtain the width of this image, you see we start from this position, and then as we go, notice how this coordinate here, the first coordinate is going to be changing while the second one is going to be somehow fixed. So you see as we move, that coordinate changes, it increases up to 1652. And then when we at this position and we instead move downward, the second coordinate is instead increasing. And if we get right here, as we move right here, you see we get up to 2198. So we now get the image width and the image height. Now to get the coordinates or the bounding boxes of a table, you see we just need to get to this point about this. We have about 100. You could check this out here. So we have about 102, 110 to 106, and then here we are about 1556, 710. Okay, so let's go back to the code. You see here 102, 218, 1547, 715. So it's approximately the same as what we had. could check this out. 1547, 715. You could get this location. This 1547, we go to the left, 47, and then 715, we go slightly up around this. So we see that with this coordinates given to us here, we are able to locate this table in the image, and this location is based on this here. That is based on this. Let's take this off. Is based on this position, this top left corner position, and this bottom right corner position. So we make use of these two positions here, this position and this position, to locate this table in our image. Okay, so we now know how to locate. We've actually seen how it's gotten, and here we are. So we have our layout, and now we have two tables, as you can see. Now we will just make use of one table, the other table. So let's search again, table. We could check out the other table. Table this, we haven't seen this. This is the second table. So we have 852, 844. Get back here, you see 850. You could check this out here still. 852, 844 about this. We'll go down, 844, 52, slightly to the left. Okay, so we are about this. See, that's the position. And then if you want to get this bottom right position, we are about this 1550, 1770. There we go. See, 1550, 1766, approximately 1770. So this is our second table right here, and clearly we have our x mean. So here we could call this our x mean. In fact, let's just copy this from here simply. So we could copy this from here, as well as we could extract this automatically. So we have here, we call this x1, so, or x mean. So let's just have that x1, and then we have y1, and then we have x2, and then we have y2. So all this is gotten automatically thanks to this Paddle model. Now we have x1, y1, and then x2, y2. The next thing we'll do is we are going to go through this full layout and select only the tables. So for L in layout, if L type is equal table, then let's print out L. So we could see this here. See here, because we have two tables, we have this two, we'll print it out. These two text blocks printed out actually. Here we have L dot block. We print out the block this time around. We run that, and you see we have now our rectangle, which is x1, y1, x2, y2. So let's devise a means of automatically getting this value as we've seen right here. Now what we'll do is we'll just we only consider this first table, this table here, or to be specific, this table here. So what we'll do is we just do a break. So from here we have break, and we just print only this one. No, we should do a break once it gets the first, not after looping the first time. So let's run that, and that's fine. Now we have this, we're interested in getting this coordinates here. So to get this, let's do L block and better understand this. So here we told let's type rectangle, and then we given the arguments x1. Okay, so here is arguments actually. So what we could do here is simply do x1, and we get the value for x1. So you see, that's it. Okay, so that's set. Now we have x1, which is equal L block x1, and we have x2, x3, and x4. We run that, has an attribute x3. This is x1 or x2 y1, or let's better say x1 y1, and then here we have y1. Let's copy this and then take this one off. So here we have that x2 y2, and then your y2. Okay, there we go. Let's run that, and then in here we're gonna print out x1 y1 x2 and y2. So we get that automatically. Okay, now that we have this, we are gonna read this page here. So let's copy pad. I'm gonna use OpenCV to read this page. So we have im cv2 im read. There we go. And then once we read that page, we are gonna crop out the required or the selected region. We're gonna crop out just this region. Now what we'll do here to crop this out, we just have image, or let's just save this. So cv2 im right, and then we'll save this as extracted image. So let's just say extracted image .jpg, and then this extracted image is this our image, but then we're gonna select certain portions. So we go from y1 to y2, and then x1 to x2. So basically what we're saying here is, because we start with the height dimension, if we're going to the width dimension, what we're saying here is we're gonna take our pixels from a given y to another y, and from a given x to another x. And then when we run this, we should have okay, here it doesn't take floats, so we need to convert this to floats. That said, what we could do right from here is simply have this ints. There we go, and that's fine. So we'll run this, and then from this here, see, we have now ints. We'll run that again, and that's fine. Okay, so let's go ahead and check out our cropped image, extracted image, and that's it. You see, we've left from our PDF to this extracted image. So now we have the table, and we're done with the first part, which is that of the table extraction. From here, we are then going on to the text detection and recognition phases. So in this text detection and recognition, we're still going to make use of the Paddle OCR, and it should be noted that this Paddle OCR comes with several text detection and text recognition algorithms. So here we have EAST, DB, SAST, PCE-NET, FCE-NET, and for text recognition, we have the CRNN, Rosetta, and all those other different deep learning models, which you can either use directly, or you can train with your own data set. Now, given that the kind of data we're dealing with here, which is this kinds of inputs, or let's just get this from the Colab, this kinds of images we're dealing with here, very common. The texture isn't very different from what you'll find in most books. We are just going to make use of this model. So now we'll go ahead and import Paddle OCR and draw OCR. From here, we're going to start with defining or creating this Paddle OCR object right here. So we have OCR, which is Paddle OCR, which is this here, which we've imported. Could simply have this. We have that Paddle OCR, and then we're going to specify the language. So we have that. Now now that you have this, we run that. We have the OCR, and then you will notice that there is this downloads. So we have this very light but very high performing models provided to us by Paddle OCR. So you see we have the detection inference, you have the recognition inference, and you also have the class, or rather the angle inference. So here you can see we have this detection inference and recognition inference. We're not going to make use of this other one here. We're interested in just detection and recognition. So once we have this tool, and we've loaded we have now our OCR engine ready, we could define the image. So let's say let's get this image from here. Let's copy this. Let's call that image. Let's define this image here, image CV, and then we'll do CV to read, and then there we go. Let's just put this image path right here. So we have our image path, and then place that out, and we have your image path. So we read our image, and that's it. So once we have that, now we could get the height, im height, and let's just say im height. So we have our image height, which is this image right here. Take the first dimension, and then we get the width. There we go. We have image CV, we get the width. Okay, so once we have this information, we can now go ahead to obtain the results. So let's run this first and see what we get. Because we've already downloaded the different models, you see it's not downloaded again. Now we could print out the image height and then the image width. Okay, so we see that we have our image height and our image width. Now from here we move on to get the result. So we have here from let's just put this out here. We have result or output is equal OCR, this OCR we have here, and then we're gonna call the OCR method, which takes in the image path. Okay, so we have that. We'll run this now, and then we'll can close this up. Okay, so we have that. We have our output. Let's print out the output. See, there we go. We have this output with the different locations of the bounding boxes and the corresponding text. So just as we had said here in the slides, you see it's going to detect or locate each and every text, and then later on, let's scroll down. Here's our deep learning model in the middle. Later on, it's going to now locate, it's going to now give us exactly what words or what sentences we have in each located region. So that's it. Let's get back to the code, and then what we'll do is we'll take output. Let's get a shape. See, we inspect that shape. It's a list. Okay, let's take the zeroth value here. Get a shape. Still a list. Anyway, let's just get the 0 value. You see here we have the box, then we have the text, and then we have the probability. So let's open this up right here. You should see that component. You see component. So we get the position, and then we get the text, and then we get the probability of that box being there. So we have that. We could simply do this. So we say for I in range len of output, or we could just say for I in output, for out in output, we could get out. Okay, so that's it. You see here we now have the different boxes with the text and the probabilities. So from here now we could say, okay, we want to define those boxes, which is going to be this 0th element right here. And so for every line in our output, every line that we have in our output, we are going to get that 0th element. Okay, so for that, so this will be our boxes now. We could run that and we print out boxes so you get to see what we have. There we go. You see we have those different boxes. Now we only have the boxes here. We have this. Let's print out for I in range length, or for box in boxes. We could print out box, so it's a bit more clearer. Okay, see, we just get only the boxes. So with this we could get only the boxes. Now the next step will be to get only, if this were output, remember we have to get also the text. So if we want to get the text, here we go, we could also get the probabilities. So let's go ahead and we get this text. To get this text, we will have text equal, we get the line, and then instead of the zero, this zeroth index, instead of the zeroth index, we move on now to the next index, which is the first index. So this index 1. So we move on to this next one. So we see here, pick 1, and then in this next one we want to get this zeroth index here. So here we have 1 0, and that's it. And then from here, still procedure for line in output, that's it. Then the next thing we want to do is probabilities. Okay, so that you should have guessed that, right? You get to this one, you get to this, and then you get now this one. So it is box line. So you have line 1 and 1 for line in output. Okay, so now let's get the probabilities. There we go. See, we have the different probabilities, and then let's also get the different texts. We have texts. There we go. We have the different texts. So now we could get the boxes, the text, and the probabilities separately. That's it. Let's shut that up, and then we move on to the next step. From here we're gonna draw this. So we'll define our image boxes, which is gonna be our image CV, and then we'll make this copy. So we run that, and then the next thing we'll do is we'll go through each and every box. For box in boxes, we are going to do CV2 rectangle, where we pass in our image boxes, and then we'll pass in different coordinates of the given box. So like here we'll have box, and then the way we get these coordinates is by looking at the way this boxes here was constructed. So a single box like this one, let's highlight the single box, as you could see, has this XY, 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 and XY. Now to be able to locate this on the image, if you open let's download this image and open it up so we could be able to locate this. So there we go, we have this open up now. Okay, so to locate this, let's look at the components. So here, for example, we would have to reduce this slide downward slightly. There we go. Okay, so we have this here. You should monitor this here. So let's reduce this again. Reduce that, and there we go. So monitor this so you could get these coordinates. You see here we are about 1510, so it's this, and then when we move here we had 111.13 around this. We move this way, 109.27 about this, and then we move this way, we are 1931 around this. So this means that the way a box is located is by going in the clockwise direction. We start from the top left, we move to the top right, then to the bottom right, then finally to the bottom left. Now to construct this bounding box, or to draw this bounding box with OpenCV, what we need is this top left and this bottom right. So what we'll be using here will be this one and this one. Okay, so that said, we'll just do box 0, that's pick this, and then we pick this 0th value. So box 0 0, let's have int convert that to integers, box 0 0 0, and then we have we have int. Let's just copy this. Then here we have the box 0 1. Okay, so we have that, and then from here we could also do the same thing we've done here. So we have this here. There we go. Oops, let's close that. Paste this out, and then here we'll move on to this one. So this is box 0, box 1, box 2, box 3. So index 0, index 1, index 2, index 3. We're interested in index 0 and index 2, as we've explained. So here we will do 2 0 and then 2 1. Okay, now that's fine. Let's rearrange this. Let's be sure that everything works well here. Okay, so we have this, and then we follow on with this one. Looks fine. Okay, the next thing we'll do now, while we're having this, the next thing we'll do now is specify the color. So here we specify the color. You could change this, and then we also specify the thickness of the boxes. So we close that. So once we have this, now we could run this. This should be fine. No, we should have your box. We should have your box. For box, there we go. That should be fine. An integer is required. Got a tuple. So let's check this out. Oh, actually this is boxes, image boxes. Actually this is image boxes, because this is our image on which we want to print out this different boxes. So or rather these different boxes. So here we have that. We run that again. That's fine. Okay, so let's do cv2. We write our image. We specify that we want to have detections, and then we have image boxes. That should be fine. So we run that, and that's true. Detections, you get to see the detections. You see here, it shows us how well our model is performing. You see, it detects all this. Okay, so now we've had this detections, and that everything looks fine. The next thing we want to do is to add the text. So here, after adding this, let's go ahead and have this cv2 put text method, which takes in the image boxes, and then it takes in the text. So we have our texts, and then for each box we have a given specific text. So let's go back here, and we take I. So we enumerate. We could do box, and then we have text in box 6, or zip boxes texts, and that should be fine. So here we have each box and each text. So that'll be it. We get the box, we get the text, and then we now see this new detections, and then we specify the location for the text, the font, the thickness, and we have the color. Okay, so we have that. Let's run this and see what we get. That looks fine. Let's check this out. See, here are detections: components, energy, water, product, and so on and so forth. See, it shows us our different detections and the text which has been recognized. Now, given that we've done with the detection and recognition, we can now move on to the text reconstruction. So in this reconstruction here, let's look at this one. This reconstruction here, we're trying to make use of the detections and the recognized texts to be able to generate a table like this one, which we could open up in an Excel sheet. Now, the way this is going to work is we are going to create this vertical. You see this vertical lines here. We have 4 vertical lines and this horizontal lines based off the different detections. So the way we create this horizontal lines is For each and every bounding box, like let's take this one and put to the side. For each and every bounding box, we're gonna extend it right. We're gonna extend this right to the edges. So we take this one, for example, and we extend it right to this. That was it. This next one, we're gonna extend it. You see, we extend this, and then this other one here, we extend it. We have that, we extend that. This other one, we also extend. There we go. So you see, after extending this, and then let's pick another line. Let's say, for example, this line. In fact, we're gonna just note that we're gonna extend each and every box here. We could pick this one. So one looks we have only 3 here, so we go faster. So we extend this to the end, we extend this to the end, we take this one, we extend this. There we go. We extend this one, we extend. There we go. Okay, so now we've extended all these different boxes. So we'll repeat the same process for each and every box we have here. Now what you will notice is that boxes which are in the same line would occupy a similar region. So like you see here, if you do this, if you bring this here and bring this here, it doesn't really look like we have 3 separate lines here, whereas we actually have 3 separate boxes, not lines. It doesn't look like we have 3 separate boxes, whereas we actually have 3 boxes in here. 1, 2, and 3 for these 3 different regions. And so the algorithm we'll make use of now will be the non-max suppression algorithm to remove this one and this other one. So we'll be left only with this, and then here we'll also remove this one and this one and say this one. So we left only with this. See, that's how we go from all these bounding boxes to just this one. And then for this one, see, we would have this here. Let's extend it to the end. See, when you extend that, you would now also take off this other boxes. Let's take them off. There we go. We would have also this other boxes taken off. Okay, so what we'll be left with will be something like this, and we'll repeat this process from the top to the bottom, or just in general we'll repeat this process for each and every box. Now the way the non-max suppression algorithm works is when you have boxes which are around the same region. Let's take, for example, let's make this simpler. Let's there we go. Let's have this here. So let's take all this off, and then we have a box. Let's have this box here. We have this box, and then we have some other box. Piece this out, and we have some other box. So when we have boxes like this, which are very close to one another, like these 2 boxes right here, we can make use of their probabilities to remove one. So like here, if we have this, let's add a third one. Let's add this third one here, paste that out, and let's say we have something like this. Okay, so this third one, you see this, we have this box here. Let's pick this box here. This box, you see, it has this probability. This other box here, it has its probability, and then this other box, it also has its own probability. So what we're gonna do is we are gonna delete this box, delete this other one, delete this one, then delete this one, such that we're left with only this box which has the highest probability of all those other boxes. Now another question you may be asking yourself is, based on what criteria do we suppose that 3 boxes are close enough for you to start deleting some others and leaving the one with the highest probability? The simple answer to this is by making use of the IOU score. So let's take this off, and then we have these two boxes. Let's reduce this so we could take two examples. So when we have these two boxes here, let's take this way. Let's reduce. There we go. Okay, so we have two boxes like this. See, each one with its own probability. Though for the IO score we don't really need the probability, so we could take this off. So we could take that off. We have these two boxes. Let's now have here, and then let's put this one this way. Then this one, there's a difference, and here we have something like this. There we go. So you see that this box and this box may come from two different lines, and so that's why you see the difference. There's the space between, or the intersection of these two boxes is quite significant as compared to the intersection we have here. So this intersection is significantly smaller than the intersection between these two boxes right here. See this intersection? See, this one is greater than this. But then it doesn't suffice to just compare the intersections, because if you have a very large box here and another very large box, the intersection may be greater than this. So what we're going to do is we're going to make use of the IOU score. Now the IOU score, IOU, let's have that here. We have this IOU is equal the intersection divided by the union. So you get the name intersection over union. So taking into consideration this union will help us in knowing how close the two boxes are. So you see that if two boxes are very close like this, the IOU will be greater as compared to this box here, because this ratio of the intersection to the union for this is smaller as compared to this ratio for the intersection and the union with this other box right here. And so that's how the non-max suppression algorithm, see the term non-max suppression, makes use of this. Let's copy this separately. Makes use of this IOU to know which boxes can be deleted. Okay, so we now understand how this non-max suppression algorithm works. Let's go ahead to create these boxes, then delete those which we are not going to make use of, such that we'll be left with something like this. But before we move on, we'll also look at how this same process is repeated to get the vertical lines. So here what we'll do is we'll go again, that's as we had before with the horizontals. We go again through each and every box and then extend it horizontally. Here we're gonna carry out that extension vertically. So like here we'll extend this. See, we extend, and there we go. We take this other one, we extend. See, we extend, and then we run the non-max suppression, which will group together all the boxes which are close to each other, and then delete all those which are not, which don't have the maximum probability score. So we have this, and you could get right up to this final one here. So we see that now we reconstruct this vertical line, or this vertical box, this vertical, and this vertical, and then what we'll be left with at the end will be something like this. So if you take this here to be a vertical box, this about a vertical box, this, and this, and then all these vertical or horizontal lines, you see, we would have something like this. Now once we have this, you see, we are now going to reconstruct our table. So let's go ahead now and put out a code which will permit us come up with this sort of grid cells right here. Get into the code. We are going to define the horizontal boxes list. So we have your horizontal boxes, and then we have vertical boxes. Okay, and then we're gonna go now for every box in our list of boxes. We are gonna extract the different boxes and add into this here. So the first thing we have to do is we define our x horizontal and our x vertical. Now what's going to be our x horizontal and our x vertical? if we get back here and we take this example, let's suppose we have this box. Are we interested in getting the X horizontal? Let's copy paste. So we would have this. Let's change the color. This will be for vertical. So we have this box here, you see, and then we want, when we extend this to the end, extend this here to this end. Let's suppose we end here. You see the X coordinate, which was here, has now moved backward. But what's important to note here is our X now will always be 0. Recall from here, if we have this box here, if we have, oops, let's get this back. Anyway, let's say we have a box here. Now if you want to get, or if you want to push this to the end, then the X coordinate here will be 0. You could check this from here. See, the X coordinate is 0. See that? 0. Now for the X, if we wanted to get the vertical line, so let's get back here. If we have this and put this here, okay, so if we extend this here like this, extend this right to the end, suppose the end is here. Now if you want to get the X vertical that's extended right to the end, you would find that it's gonna maintain its same X coordinate. So those boxes, you see the initial boxes we had, is gonna maintain the same X coordinate, because the distance from this here, from this edge here to this X coordinate remains the same when we extend this vertically. But when we extend it horizontally, this distance here, you see the bounding box moves from this, the X moves from this to this here. So this means that in the code we're gonna have our X horizontal, which will be 0, see, and our X vertical, which will be the same value of X we've been working with so far. So that's it. Remember, if we have a box, let's say we have boxes 0, you see, remember here, this is going to be our X and our Y, and then this is going to be our X and our Y for the bottom right position. So here we have box 0, 0 to get that, and then we move on to Y. Now for Y, we have the Y horizontal and the Y vertical. Let's get back here. If we take this, let's move this a little. Anyway, let's just leave it this way. So what we're saying is we have this horizontal, oops, we have this horizontal here. Now the question is, what has changed in the vertical position? You see that before we had this box which was here. See, before we had this box here. Now after extending, you notice that the vertical position hasn't changed, so the Y position doesn't change. Now if we get back here, you see our Y horizontal remains the same. So that said, we're gonna still have int box 0, 1. So we still have this same value. And then for the vertical, our Y vertical, let's get back here, our Y vertical, now we'll take this off. Our Y vertical, given that we had a box which was initially this, see, the box was initially this. Now when extended to the end like this, the Y coordinate has moved through the whole image, and so our Y vertical here would be the height of the image. So here we're gonna have let's get back here, we're gonna have the image height. So remember, we had defined the height previously. Let's get back to get that exact. Here we had the image height. Okay, so we have the image height, not just height. So here we have image height. Okay, so that's it. We understand how to get the X coordinates, the X values, and then the Y values. Then from here we can now get the widths and the heights. So after getting the X and Y coordinates, we now get the widths and the heights. Let's start with the horizontal again. So let's shift this way, and then we get back here. So now we've extended this to this end. To get the width of this box, you see the width of this box is simply the image width, and then that will be it. So here we have the width, for the horizontals is going to be the image width, and then the width for the verticals, is going to be from here, the width for the verticals, we could shift this way, get this back. So initially we have this box, now we have this vertical, and we're trying to get the width for this vertical. The width here will simply be the difference between the x mean, the minimum x, that's the x for this, the x at this position, and the x at this other position. So we get this difference. So if we have this x at this position, we can get the x at this and then subtract to obtain this width vertical. We get back to the code. To get this, we just simply have int, we have box. See, we have, no, this is 2. So because we want to get this x, subtract with this to obtain that. So we have 0, there we go, minus box 0, 0, and that's it. That's how we obtain the width for the verticals. Now once we have this, we move on to the heights. So we want to get the heights for the horizontal and then the height for the vertical. Now for the height here, this should be the image height. Let's take this off, and then we take this off. Okay, so as we're saying, this height for the verticals, if we get back here, the height for the verticals, we have the vertical, the height is simply the image height, so that's easy. We just get here, and then we have image height. There we go. And then for the height for the horizontals, we shift this and get back to this one. The height for this horizontals is simply the y coordinate, this first y coordinate, and then the difference between this first and this last y coordinate. So we get this difference here. So to obtain this last, we just simply have something similar to what we had already here. We have box 2, 1 minus box 0, 1. So that's it. We see we obtain that height now, the height for the horizontals and then the height for the verticals. So once we have this set, the next thing we want to do is construct our horizontal boxes. So we just have there we go, we have our horizontal boxes that append. Now we're gonna append the x horizontal, the y horizontal, and then the x horizontal plus the width. See, for this, for example, since you know you already have this coordinates here at this point, so now to obtain this coordinates here at the top, at the bottom right corner, it just suffices to get the x, this one, plus the width, and then the y plus the height. So you shift to the right and bottom, so the bottom right, and you end at this point here. So with that, you see we have this here. See, x plus height, x plus width, sorry, and then we have y horizontal plus the height. You see, that's it. There we go. Now this is height horizontal, so we should be careful with that. Height horizontal, and then here we have width horizontal. There we go. Now I think we should change this here. So this is width, and then here we have height, and then height. Okay, so we have that. Okay, so we have the x, y, x plus w, x plus width, and then y plus height. Okay, so that's it. We have the set. The next one will be for the vertical. So we have vertical boxes. There we go. We append that, and then we do the x vertical, the y vertical, obviously, and then we get the x vertical plus the width vertical, and then we do the y vertical plus the height. It's actually the height vertical. So that's it, height vertical. Take this off. Here's the x vertical plus, see, x vertical plus the width vertical. Okay, so we have this set now. We have the horizontal on the vertical boxes, and that's it. So we could simply run this here. That's it. And you see now we could have this. Let's have this here. Let's say we want to have horizontal boxes 0. See, for the same boxes, he has been transformed to this horizontal line. See, 0, 13, 6, 98, 31. Now it'll be interesting for us to be able to actually visualize this. So what we're gonna do here is we're gonna have this image. So we'll define, let's get back here. We have this horizontal boxes here. So let's add this. So we'll call this image, and then the way we'll define this is we're gonna have a copy of our image, of our initial image. So we copy that initial image. There we go. And then let's run this. And then what we have here is we apply the rectangles. So rectangle, we have the image here, that's it. And then we have x, h, y, h. There we go. And then we have x, h plus w, h. Basically this here. So let's just copy this. We want to have this, and that will be it. Okay, so we copy that. Oops. Paste that. That should be fine. So we have x or y, x plus w, y plus h, and then we will specify the color. So let's say 02550, and then the thickness 1. We repeat the same process for this next one, for the vertical boxes actually. So here we would have this xv. So this is v, yv, then xv plus the width v, yv plus height v. Then let's change the color so you could see that difference clearly. It's preferable 0255, and here, oops. Anyway, we should have 0255. Okay, so we have that set. Now let's run this and see what we get. See, that's our image. Now let's go ahead and do cv2 in right, let's say horizontal vert .gpg, and then we have our image. We run that, and let's check out what we get for our image. This should be fine. Okay, so let's check out horizontal vert, and what do we get here? Okay, so you see we have the horizontal lines, but we don't get the verticals. So let's get back and be sure that everything works well. So what we do here is we're gonna comment this and visualize this again. You see we have no box. Let's look at this. We have no box. Let's increase this here. Let's increase this thickness. See what we get. Still no box, but we see we have this here. This means that there's a problem with the coordinates. Now if we check at this looks fine. The image height, the width v is this, looks fine, and the yv here, this shouldn't be the image height. This should be 0. Reason being that when we get here for a vertical box like this one, to get the y coordinate vertical, it should be a 0. So given that you extend it right up to the end, then the first y coordinate, this coordinate here, the y should be a 0. So that should be the problem. Let's run this again and check this out. Okay, so you see we detect those. Now let's reduce this and then get back right here. Run this again. Now let's get back here. Do this copy. Run that. Check this horizontal, and that's fine. So you see now we have the horizontal and the vertical lines. Now what we'll do is we're gonna apply the non-max suppression to take out the lines like here, to leave out actually only a single vertical line. You're only a single vertical line, and you're only a single vertical line. So let's take that off, and then we move on to the non-max suppression. Now that said, we're gonna use TensorFlow's non-max suppression method. Here we specify the horizontal boxes. So all you need to do is specify all these horizontal boxes. There we go. Once you specify the boxes, you give the probabilities, because we'll be making use of the probabilities to remove the other boxes. We don't have the max probabilities, and we have this IOU threshold. So this is from here. Let's get back here. If you recall, when we explained the non-max suppression, we're gonna suppose that two boxes belong to the same line if the IOU threshold is actually greater than 0.1. So that said, we'll get back here, and then let's call threshold negative infinity. Okay, so let's just have this, and then we run it, and then print out our horizontal out. So let's get this. Let's print this out. Oh, let's print that out. Take this off. See what we get. We see that we have a length of 37. Now what we'll notice is when we open this up, this length of 37 should coincide with the number of lines we have here. See, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We ended at calcium. 19, 22, 25, 28, 31, timing, 34, 37. Okay, so you see we have 37 lines, and that's why we have this here. Now, so this represents each and every line. So you see this represents each and every line. Now what we can do is we could sort this out, and so we would have horizontal lines, which is np sort. We'll convert that to an array. Horizontal out. Okay, so we have this. We're gonna sort this, and then we'll print out our horizontal lines. And now this has been sorted out. You see that we have box 0, box 3, box 5, box 10, box 13, up to box 108. So if we do boxes 0, see, this is going to be you see, first box, and then boxes 3 will be our next box, boxes 3 will be our next box, see, so on and so forth. Now what we could do here is also visualize this like we visualized this horizontal right here. So basically what we could do is we have for I in range length horizontal lines, or basically for val in horizontal lines. See, we get for each and every val here we are going to have, let's do im non-max suppression. We have our original image. There we go. We copy that, we run this, and then we will do this rectangle. Let's get back here to this rectangle. Okay, so we'll have something like this. Copy this out, and then here space this. We'll do cv2.im right im rather the im nms gpg, and then im nms. Okay, so we have that, and then here we have im non-max suppression. So we have this val. See, every time we get one of this, we have the val. See, we have the val instead of the box. We have this val, which are those different boxes in the line with the highest probability scores. Okay, so that's it. That looks fine. We run this, and then we run this. And the invalid index to scalar variable. Let's check out the issue here. If we do print val, you see the values we have in here are actually this different values. So we actually supposed to do that box. So we're supposed to have that boxes and not that. So we select a box like 0. See, we pick out a given box, and then we get its value. So you see val. So it's boxes val instead. Boxes val. There we go. Boxes val, and finally here we have boxes val. So this should be fine now. Oh, we have that. Let's take this off, and then we visualize our image non-max suppressed. So there we go. We have here, and that's what we have. You see, what we get in here, if you notice, is just a box for each line. So this here is for this, this is for this is for that, and so on and so forth. But what we're supposed to do here is, instead of having this boxes, we should take Horis boxes. Horis boxes. There we go. Horis. Horis. And finally here we should have Horis. So as we were saying, this here represents all the boxes with the highest probabilities. So you see, these are the boxes with highest probabilities. Now when we do the Horis boxes, we'll get the boxes which occupy the full width of the image. Let's run this again and see what we get. Getting an error, not subscriptable. Let's be sure that we had this right. Horis boxes. There we go. Horis boxes, and that was it. Anyway, let's do print Horis boxes a given val, and no, we should take this off. Print. Let's check that out. Int is not subscriptable. So you see, we actually get this. We actually get the Horis boxes, but we should get just this value. Okay, yeah. Remember, the Horis boxes is given out differently, or has different format with the boxes themselves. The boxes, we hope we have this here. This reconstruction. Here we have the image boxes. Let's just put that somewhere here. So we have here Horis boxes, and then we have image boxes. Image boxes. You see that the structure is different. No, this is boxes, not image boxes. You see that the structure is gonna be different. Like you see here, see this is the x mean, y mean, x max, y max. That's the top left, bottom right. But here we have top left and bottom right here. So because of this difference in formatting, we have to be careful when using it here. So here we have Horis boxes val, and then we pick out 0 simply. So yeah, that's it. We have 0, and then here we have 1. See, we have 1. Here we have 2. We just take this off, and then here we have 3. Okay, so we have that. Let's run this again, and hopefully now we should have no problems. Syntax error. Why are we getting this error? Let's check this out. See that? That's fine. Oh, it should be this one. Looks fine now. Take this off and run that again and visualize now. Okay, so let's check out this one, non-max suppressed image, and we get this. You see, that's what we get now. See, we only have a single line. So we've done the non-max suppression, and we've gotten each and every line. So we see that we have 37 different lines. Now this same process can be repeated for the vertical lines. So we just repeat that by the same non-max suppression, getting the vertical lines, and then sorting it out, because the sorting is very important. Then that will be it. So there we go. We have this vertical out, and we specify the vertical boxes and the probabilities. So let's run that, and then we print out vert out. Yeah, we have that, and see what we get. See, we have just 3. See, we have just 3. So this tells us that this we could get this from the box 52, box 45, and box 1. So you see, we have just 3, which is for obvious reasons, because we have actually just 3 columns here. We have 1, 2, 3 columns. So that's it. We get this 3. You could repeat the same process to visualize it like this, but we're gonna skip that for now. Or let's just try to do it, because it's gonna be helpful for you to understand how this works globally. So let's take from here. We're just going to go through as we had for this, and we have this here, so we could paste this out here, and then we have this. Then we do vert lines equal np sort. We get the vert out, just as we did with the horizontals. So we have the vert lines here. Let's print out vert lines. There we go. Now here we should have vert lines. That's fine. We've replaced all these horizontals by verticals. We also made a slight error here where we had 2 instead of 3. We've modified that. That's fine. We'll go ahead to run all this again, so we should be able to visualize our image now with the horizontal and the vertical boxes. Okay, so you see, we have horizontals and we have the 3 verticals. Now, given that we want to take each and every element we have here and put this in some sort of array, which can then be saved in the CSV format and read in an Excel sheet, what we'll do is we're going to create this array. But first, we'll suppose that the elements which make up this array are simply empty strings. So let's shift this, and then we see we have this array created right here. Basically, what we're saying here is we go through the vertical lines and then the horizontal lines. So here, let's run this. Let's get the shape. Let's get the shape. You see, we get the shape. This should be 37 by 3. It's a list, so we should have, let's convert this to an array so we could get the shape. There we go. We have that. So we have 37 by 3. So here you see we have 37 lines by 3 columns, and what we'll do now is for each and every line, so take note of this, we'll go line by line, and then for each line, like say this one here, so let's consider this line. See this line. So for this line, we are gonna look each and every vertical line. So we pick out a line, and then we go through all the different vertical lines. So obviously we would have 4 vertical lines here. Let's just put this out here. We have this one, and we have this other one. Let's add this one here. There we go. You see, we have this 4 lines. You see, we have this. Now let's pick this one, this horizontal line. As we've said, we're going to go for each and every horizontal line. We're going to pick now each and every vertical line. For this vertical line, for example, we're going to get the intersection of this horizontal with this vertical. So clearly this intersection is going to be this here. Let's draw it so you could see that this is going to be the intersection. There we go. You see, that's going to be the intersection. And so now we get the intersection of this with this. Remember, we're going to go through each and every line here. So for this line, we get this intersection. Let's also do this here. Although here we would have no word or no text actually. Here we get this intersection of the two. See, this is for the first line. We get this intersection, and this intersection with this one. So once we have that intersection, the next thing we'll do is we'll then compare with each and every box. Remember, we've had all the different positions of all the boxes. So we compare for a given box and see which box is coinciding with this intersection. It's clear that the original bounding box we had here is going to have a high IOU. Remember, the IOU, intersection of our union, is going to be like this, as compared to another box which we just will pick at random. So if we pick, let's have this here. See, so the IOU between this box and the original bounding box of this text will be greater than the threshold. And if you compare this original box with another box, you wouldn't get that. So simply we just get the box which has the max IOU with this box. So we get the box which coincides the most with this box. And once we get that, it means we have extracted the text, because for every box we know its text. And since we know its text, we're going to replace now this output array. Remember, this here we're going to replace this empty string with that text. Let's say, for example, component. You see, that'll be it. So what we're saying here is we're going to go for each and every line, repeating this again, and then we compare each horizontal line with the vertical lines. We get the intersection. Like here, this is going to be the intersection, and you see that it's only this text, or this text is going to have the highest IOU with this intersection right here. And then for this position, we're going to have the text component extracted. So let's close that up. We see we have our output array, which when we print out array, you see it's all empty strings with 37 different lines, and each line having 3 columns, as we could see right here. So now we're going to go through each and every horizontal line, and for every horizontal line we'll go through each and every vertical line, and then from here we will obtain this resultant, which happens to be the intersection of our horizontal and our vertical line. Now let's have here horizontal boxes actually, because here let's have horizontal boxes. We have all our different horizontal boxes here, which we could see, and then the horizontal lines corresponds to the boxes which have the maximum probabilities, which we have seen already here in this in non-max operation. So each and every one of this produces a box. That's why we have many horizontal boxes, or many elements in horizontal boxes, but only those with the highest probabilities are retained. So that, and those form the horizontal lines, which we can see here. And so that said, we want to get the intersection of this line with each and every vertical line. So that said, we'll get back here. We have horizontal boxes, and then horizontal lines, and we specify. Let's reduce this here. Horizontal lines, and we specify that given index. See, that's it. That's why it's important to sort this, because sorting permits us to start from the very first one right to the last. Okay, so that's it. We have this already. We have the horizontal line. The next thing to do will be to get the vertical line. Okay, let's check this out. So here we have vertical boxes, and then we have vertical lines, and then we pick out here J. So we now compare this with each and every one of these vertical lines. That said, let's define our intersection method. So here we have intersection, and then what intersection does is it takes in a box 1, another box 2, and then it outputs that intersection simply. So let's return the intersection. Now this intersection will be basically this here. Let's get back to this. So what we'll do is we'll say, okay, we have this horizontal. Let's take this off. We have this horizontal line and we have this vertical line. To get their intersection, we need this point here, see this point, and we also need this point just right here. Now the x coordinate of this point coincides or corresponds to the x coordinate of the vertical line, and the y coordinate corresponds to the y coordinate of the horizontal line. You see, if I move downward up to this, it corresponds with the y coordinate of the horizontal line, and for this point the x coordinate corresponds with that of the or the x of the vertical line, and the y coordinate, that is if I go downward, corresponds with the y of this line here, of the vertical line. But you should know that it's at this point, so you have to be very careful with that. Now that said, what we have here is box 2. So we have this box 2, that's not box 2, we have box 2. Yeah, we have this box 2. This is horizontal and this is vertical. You see, horizontal and vertical. So the vertical will be the x, and then we have its x coordinate. Then we have box 1, its y coordinate. That's it. So we have x mean, y mean. The vertical x and the horizontal y. Confirm that here. The verticals x, there's a vertical line, it's x, we'll go this way, x, see, from 0 to this x vertical, and then for the y we go from 0 downward up to this, corresponds with the horizontals y. So that's why we have that here. And then the next we'll do will be box 2, the verticals second, that or rather second index. Actually this second index corresponds here to its y max, so or rather it's x max, sorry. So we have box 2, the vertical is x max. See, its x max is this distance from here right up to here, distance from here to there, this actually here, so we could say from here to here, it's the same distance actually. So all you need to understand here is we go from 0 to x max of the vertical, and then to get that's how we get the x coordinate of this point, and then to get the y coordinate we go from 0 downward up to this point, and that corresponds to the x of the horizontal line. So let's get back here, we have that, and this y coordinate here, this distance, corresponds with the y of this horizontal line. So getting back here, you see we have box 1, that's horizontal, and we get its y. So there we have box 3. Okay, so we have that set, we have our intersection, we get the resultants, and let's print out this different resultants. There we go, print out the resultant. See, that's it. That said, you see 14, 434, 51, 457. We could check that out quickly here. Let's get this. There we go, we have 14, just check this out here, 14, 434 xy, 14, it doesn't match actually. 434 is around this here, 434 is around here. There is a problem, see, 434 is around this, so there's some problem here. Let's increase this and push this way. Here we have about 434, 14 around here. So this means that it coincides instead with this box. What we get is inside this box, because if you get the year 67936. So now we could see the resultant. We have 295, 13, 334, 31. Let's check that out here. It doesn't correspond to this, it corresponds actually to this one here. See, 295, you could see that here, 295, 13. Then you look at this here, we have 342, 28, approximately this. So this corresponds, this first one, it's actually the first, it corresponds to this second box instead, whereas we're going for each line, want to go for each and every vertical box. Now let's look at the next one, 446, 13, so around this, 484, 31, around this. You see, this is 484, 31, this corresponds to let's check this. No, it's actually this 484.31. Doesn't get there. Okay, it's around this because the intersection or the vertical box was like this, not up to this end, so it should be around this. So here we have 492.40. So you see corresponds with this one here. Now we see we have this intersection, but our problem now is it is unordered. For the horizontals, it's ordered because the way the initial algorithms, the way this text detection and recognition algorithms work is they go from top to bottom. So it means that for the horizontal lines, they are already sorted. So if you get this line here, if you get this index for this box, it's already sorted in a way that you don't need to rearrange them. But for the verticals, it's possible that when you have, let's say, 3 vertical boxes, and then you're trying to create those lines with your non-max suppression algorithm, it may happen that the first vertical box you get will be this one in the middle. And so we have to make sure that the first vertical box becomes this one and not this one, so that when running through or when recreating our table, we should have this outputs making some sense. So let's get back here and try to reorder the vertical boxes. To again understand what we just said, you see this here are vertical lines. You see after sorting we have 1, 45, 52. It looks normal, but when we take this here, let's take this image and put this side here, you see that this box 29510, 29510, let's go 295. 10 should be around this. 29510 is about this here. It's around here. So you see this is the box. This box here, that's after sorting, box 1 corresponds to this. So that's it. It corresponds to this box right here. Now box 45 corresponds to 446,390. It's about this. No, it's about 446,390. We need to go downward about 446,390. Let's go down. 446. It's about here. See, it's about this box. So this is the box which provided our vertical line, and then here this box provided our vertical line, meaning that this box had the highest probability and this other box had the highest probability for these lines. Now it happens that this one came before this one, and then this one comes last. So instead, what we want to do is something ordered. Here you see 14, 462, 14, see 14, and then 462, go downward. It's about this here, see, about this. So this is the box which provided our position or our vertical line here. So what we're having now is this has been sorted in this vertical direction, because you see this is the first, this is the second, and this is the third. But what we need to do is instead sort this in the horizontal direction, such that this will be the first, this will be the second, and this will be the third. For the horizontal lines, we don't face any problems because this has already been structured in a way that this here will always come before this, and so on and so forth. So that's no problem. But for the vertical lines, we need to reorder this such that we consider this direction instead of this direction. Now more concretely, what we're saying is when we have this vertical lines as we have here, and that we're going through each and every vertical line here, that is in J we go 0, 1, then 2, that is we'll go through this one, go to this next box, and then this other box. We now have to sort this such that we instead go through this box, then this one before this one. So what we want to do now is convert this into 2, 0, 1. You see, that's what we want to have. That said, now let's sort this box right here based off its position in the horizontal direction. To do that, we're gonna have this unordered boxes. So we have unordered boxes, and then for I in vertical lines, we have this unordered boxes here, which we're gonna append the values we get here. So we have for this unordered box, for example, we're gonna attach the vertical box. So we add this vertical box, vertical boxes I, you see, pick that I, and then we're gonna get this x coordinate, and you're gonna see shortly why we need this x coordinate. Let's run that and then add this code. So right here, let's print out our unordered boxes. See, that's our unordered boxes, basically what we expect. See, let's print this. Let's print this I here. Let's print vertical lines I. Vertical lines here, that's fine. We print out the vertical boxes. Let's run that. See, we have our vertical boxes here. Now what we want is this second index to go to the 0th position, as we've seen here. The second should go to the 0th, and then this one goes to the first, and this one goes to the second. So that's what we want to do. But to do that, we are going to make use of the unordered boxes. So this unordered boxes here, if you notice, takes only this x coordinates. And if we get back here, you'll see that in order to sort this such that this comes first, this comes second, and this comes third, all you need to do is just get this position here. You get this position, you get this x coordinate, you get this x coordinate, then you compare them based off your x coordinates. And that's what we're doing here. We're comparing this based off this x coordinates, this here. And if we have that now, see, we have this, we have this, we have that. We are now going to create an ordered box. So here we have ordered boxes, which we're gonna have as the arg sort. So we have arg sort of our unordered boxes. We sort it now with respect to this x coordinates. So let's have that, and we print out our ordered boxes around that, and you see we have now 2 0 1. So we've gotten that order which we needed, and you could always test this with different images. So we left from 0 1 2 now to 2 0 1. Let's take this off, and now we're ready to modify this right here. So every time we go, instead of J, we're gonna get ordered boxes of J. So when we had 0, we would have 2. See, we have 2. When we had 1, we would have 0. When we had 2, we would have 1. So this permits us to map from the unordered boxes to the ordered boxes. Okay, we run this now again, and we should get something better. Scroll up. There we go. See, we have 14. See, at this point here, 14, 14, 13, 51, 31. There we go. Something around this, around 50. Let's use this different tool. Let's get back so it's clearer. Increase that. You see, we have 19, around 14, 13, and then here is about this 106, 30. Anyway, it depends on the box which represents all this. It should be this one. So if it's this one, then this here, this distance, here we have a 124, 34. Here is 51, 31. Let's go 14, 13. It's about this. That's fine. We go 51. Let's go this way. We stop around here, 51, and then we have 31. 31. We go slightly downwards, about this. Anyway, we see that the box is around this. So this is our intersection. So now we have this intersection. The next thing to do will be to compare that intersection with each and every box and see which box corresponds to that intersection. Now the way this comparison will be made, as we've said already, will be by using the IOU score. Now the IOU here takes in two boxes, box 1 and box 2, and then it computes the intersection and the union. Here we have intersection divided by union. The way this intersection is computed is by making use of the box parameters. So to get this intersection here, let's look at this. This intersection is x2 minus x1. That's a max between x2 minus x1, such that we don't have this difference, or we don't have negative values. So this permits us not to have negative values. Now the way x2 and x1 are gotten is by getting the max of the x coordinates of the two boxes, and here is the max of the max x coordinates of the two boxes. Now let's explain. Let's get back to this here. You see, at this point right here, let's add some text. Let's copy this here. At this point, we have x mean, y mean at this point here, this point, and then let's reduce that. And then at this other point, we have x max, y max. Or let's just generalize this. Let's put this here for the two. That's x mean, y mean, and this is x max, y max. You see, that's it. So now we have x mean, y mean, x max, y max. To obtain this intersection, we need to get this point and this other point here. Not this point, not this one, but this one here, this one right here, and this one. Now to get this one, what we need is the maximum of the two minimums. So here we have these two minimums here. We need to get a maximum x of the two minimum x's. So here the maximum will be this, and then here to obtain the x here, we need to get a minimum of the two maximums. So the minimum will be this one here, see, and it will coincide with this point. And then for the y, we need to get the maximum of the two minimums. We have this, you see, we fall on this point. These are the two minimums here. These 2 points here, top left, two minimums. We get a maximum. Y will get this point, and then to get this here, we get the minimum of the two maximum y's, which will fall on this here. See, it's going to fall on this point. These are the two maximum y's. With distance from here to here, distance from here to here, the minimum will be this one. So we'll fall on this, and that's how we get these coordinates. And once we get these coordinates, we have this intersection. See, that's it. Now to get the union, all we need to do is to get is to add this up, the area of this box plus the area of this box minus the intersection. So we don't calculate the space twice. Okay, so that looks clear. That's what we just did here. See, x mean, for the means we have the maximum of the two. For the y, you see this is 1 the maximums, and then for the x2 y2, that's the max. To get x max, y max, we need the minimum of the two coordinates, and that's how we get the intersection. Because here, let's get back here. To get this area, all we need to do is to take this x max minus this x mean times the y max minus the y mean, because that's we get the width times the height. Let's get back here. That's what we've just done. See, that's it. Now if this intersection is 0, it returns 0. Simple. You see here we get the x max minus x mean times y max minus y mean. That's it. And we'll do the same for the box 2, and then we compute this. So let's run this IOU. We've already run, oh no, we yet to run this because we still have some work to do right here. So what we're saying is now we have the IOU and we have the resultant. We'll be able to compute the result, or we'll be able to compare each and every box. So for I in range, length of all the boxes, or let's say B, because we used I already. For B in range, length of all the boxes, we are gonna get the specific box. There we go. You see, remember the box notation was a bit different from the usual notations we have in here. So we will have to get x mean, we have 0 0, and then here we have 0 1 for y mean, and here we have 2 0 and 2 1 for y max. So that's how we get the box. Once we get the box, the next thing to do will be to compare this IOU. So we have if the IOU between the resultant and the box is greater than 0.1, what we're gonna do is we're supposing that, or we now know that this is the box in question, and so we're gonna have the output array ij corresponding to the line and the horizontal line and the vertical line. So that's it. We have ij, which now is our text b. because this remember we had already, let's run this here. We have texts, we run that. There we go, and each text is for each and every box. So we have this text here. So if the box matches, then what we do is we make sure that the output gets that. So we have IJ. So let's open this up. There we go. We have this. So we go if this coincides. So if this here, this box, this intersection coincides with this box, then we get the text for this box. That's it. That's why it was very important for us to make sure we sort this correctly, because without that sorting, then we would have this ones coming before this, which is not what we expect. So this is this looks fine. Let's run this. That's fine. Yeah, and then let's look at our output array. There we go. Here's what we get. See, we have component, unit, borrowed analytical data, energy. See that all these values which have been extracted and in the right order. Now the last step now will be to convert all this information into our CSV. So let's have that. We've imported pandas here. So import pandas as PD. So that's what we're using. We're using pandas to convert this or to put this information in our CSV. So let's open this up, and Colab permits us to visualize CSV, so there should be no problem here. See, that's it. There we go. See, oh, that's it. See, we left from let's compare this to. See, we've left from this. No, this one looks too big, so we shall use this one instead. Let's get back. There we go. We reduce this one, and then we compare this here. Okay, so what we're saying is we've left from this, see, to this. Now we could compare this side by side, get some qualitative analysis. Let's go this way, and then check this out. See, component, unit, borrowed analytical data in percentage. That's it. Energy, see, that's it. The water, all of that. So it gets practically all the information. See, here there's not a space, here there's also a space, so on and so forth. So you see how we've been able to extract this information from this table. And now what you can do is create a full pipeline where you just takes a PDF and outputs all the different tables in some separate CSV files. So anyone who does this, that's who writes a method which will take just the PDF and output all the different CSVs which contain all the different tables, we get a scholarship for one of our courses at Neural Learn. So here you just what you do is, if you get that, you get here, and then you by mail you're gonna send us a message telling us or showing us your Colab which actually works, which we shall test. If that works, then we shall give you a scholarship for any one of our paid courses.